All right. All right, welcome back. The voice is coming in. Today, we will cover the regular final class lecture led by Dr. Min, Geob team, and the discussion led by Seung-Jae Lee. And then tomorrow, there will be a trip to Kriso, starting from not this time, around 13, shorter than before. So there are 14 students coming together, including, and then two TA myself. So altogether we are 17 people. I guess you are coming who are joining the trip. I know that another announcement coming from TA. I also got the same information. There are the 4 cars are driving, and each car has 3 additional students joining. We have a small technical problem here in the classroom PC. So we don't have a screen not available at the classroom. Right. So camera is not also okay. I want to show you small experiment on water displacement, stability, and weight and cargo. Students. So you can say this is a ship. Ship made of steel plates, and also it has their own weight. We call this a lightweight of the ship. So that when it is floating, then there is a small drag because of the lightweight. There is a force balance between water and the object.
the ship. So that when I push down the ship, the gravity will be increased, but also the buoyancy force is returning back to my hand. That is also balance between force and water in this case. You can think this is coming back. So it's loaded onto the ship, and the displacement should be, the direct line should be moved down and increase the displacement to compensate the force coming from the cargo. So still there is another balance, right? There is another balance. And then you see that freeboard is not so large now, right? So if I decrease or load more powers on them, and then there can be a more direct line. So freeboard is decreasing, so that you can say this is not safe situation. Until it is, and you sink down. Oh. Then finally, this one can be happen. You cannot make the ship is balancing between cargo weight and ship weight and displacement. So it can be a disaster. Now, this one looks like a submarine. A submarine. So you may know that this one is floating when there is no weight, no buoyancy, no ballast water. So you know that if you want to submerge, you need to have a neutral buoyancy. Neutral buoyancy, you need to know that about this. But I guess this one has a plastic coverage, not steel plate, so that the neutral buoyancy can be obtained almost full fill of water inside. Still, it is good. So it is moving down, but still we are staying. I don't have a swing, but it's not easy to. Anyway, you should. So for the submarine, it is not easy to make a stable position. Because all the weight and then balances are moving down, even though we have a more water inside. Well, I hope it can be a neutral. Let's see. No, it's not it. And there is another sample. This is a toy, right? But it has very good stability, so that it never falling down, right? Falling up upright position again in any condition. Right? So you may think of that you may make designing or building a ship like this one. Then the ship is every time is safe, right? And actually there is such a ship for the patrol ships or coast guard. They need to patrol around the coast to make save the life. Even though there's a storm coming, they should go to the people who has a problem, so that they need to have a very good ship. They never fail, even though a very bad condition. So there is such a ship, several ships around the world. who usually have a Coast Guard has such a ship. The problem is inside the ship. The people inside the ship is not good in quality because it's too, what can I say, too much movement. So that the people inside can be hurt because of the acceleration. Much exposed to the motion. So there is you need to have a balance, but safety and also safety for the people in the ship, ocean, but also safety for the crew members inside the ship. All right, that's it for me to show you something today. What is the chatting here? Okay, that's the explanation, right? All right, so then we may move on to regular condition. Also, I guess TA spread out this sheet, similar one to the people who are coming. You may have these car numbers, and because you need to know that which car you need to join and who is the driver. So you need to contact each other, drive at the same time. Okay, then we may invite Dr. Min, who is right coming. I have his lecture note already. Model test, right? This one. Okay.
Hello, this is Dr. Min, and today I'm going to present about model test. You can refer resistance and powering part from the book. And here is today's content. Model basing theory was invented by William Froude in 1868, and since then, prediction of ship resistance based on model tests were possible. It was possible by dimensional analysis and using similitude. As shown in below figure, from experiment of small-sized models, we can predict the resistance of real ship. This is a video example of model test basin.
Learn by doing.
The Model Test Basin AMC is one of our suite of hydrodynamic facilities. This particular basin focuses on operations of ships and boats within coastal regions. Virtually all of the work that we do looks at when they're operating in shallow water and the effect that shallow water and waves, for example, can have on that boat or maritime structure. Our basin has got a number of features as far as what sort of test we can run. There is a multi-element wave maker. It can generate anything from very simple waves through to very, very complex waves. It also has a gantry from which we can tow ships and a number of quite novel and unique measurement techniques, ranging from digital video motion analysis to get the motions of multiple bodies, and even right through to things like laser diagnostics, where we can look at fluid flows down to the nth degree. At the Model Test Basin, we test a wide variety of different models. The obvious ones tend to be floating or some form of sea-going vessel, but it does extend well beyond that to look at things like oil and gas platforms or, for example, into marine renewables, where you might be looking at some form of offshore structure. that's trying to convert the energy in those ocean waves into usable electricity. Our undergraduate students make good use of our facilities right from semester 1, first year. There's no better way to learn than to actually get in there, get your hands dirty, understand what's happening, look at waves up close, and to also be able to create your own models and see how they will perform in a real sea state.
Dimension, we can predict real ship dimensions from model ship. Well, model ship experiment by dimension analysis and simulation. Dimension analysis is the analysis of relationships between different physical quantities by identifying the base quantities and primary dimensions and initial measurements, and tracking these dimensions and calculation of different problems. Primary dimensions in mechanics are mass, length, and time. And for a single pendulum in the flow, relevant physical quantities to tension of string are mass, length, and gravitational force. For applying dimensional analysis to ship resistance, resistance depends on the following physical quantities such as fluid density, speed, size of body, weight, viscosity, gravity constant, and pressure. Similitude is the study that allows us to predict the quantities to be expected on a real ship from measurements on a model. Functional relationship between a set of non-dimensional groups, we can predict the corresponding value of resistance. There are two main types of resistance, which are frictional resistance and residual resistance. Frictional resistance comes from motion of flow through a viscous fluid, and residual resistance is sum of wave masking resistance and eddy resistance. Wave masking resistance comes from energy that must be supplied to the created wave, and eddy resistance comes from the energy carried away by eddy's shed. For minor resistance, there exists air resistance, which comes from aerodynamic drag acting on the above water part of the ship. Proud constructs hypothesis that dynamic similitude for both friction and wave masking cannot be satisfied at the same time. So the practical method is to deal with frictional and wave masking resistance separately. His hypothesis is that the total resistance is the sum of residual resistance and frictional resistance, and it must be dealt separately.
화면 디스플레이를 다른 디스플레이로 스위치하시겠어요? 지금 중에 송출되는 게 이 화면 송출되는 거. 문제고 다시 여기서 네. 제가 바꿨어요. 이게 안 나오고. 음, 네. 그냥 할게. The shown equation is Fro's law of comparison and that ships of different size will have the same residual resistance coefficient, which is CR, if they are moving at the same value of parameter V square over GL. This parameter V over square root GL is called the fruit number, which is non-dimensional parameter with symbol Fn. And for deeply submerged body, the frictional resistance is dominant and frictional resistance coefficient CF will be the same for model, and the ship provided that the parameter VL over nu is called Reynolds number, and also it is non-dimensional parameter with symbol Rn. So predicting ship resistance procedure is as following. The model is made to a linear scale ratio of lambda, which is length of real ship over length of model ship. And we can run over a corresponding speed, which is model speed, that is speed of real ship over square root lambda. Total model resistance can be measured by experiment, and frictional resistance can be calculated assuming that smooth flat plate of same length. Then residual resistance of the model can be calculated by subtraction of total resistance of model ship to frictional resistance of model ship. Residual resistance of the ship is calculated using a frictional coefficient chart. Then finally, total ship resistance is given by adding frictional resistance of real ship and residual resistance of real ship. Power requirement can be also provided by multiplying total ship resistance of real ship and speed of real ship. So this is end of my presentation.
No question? Okay, for the basic problems.
Going without using this PC, right? All right, then we move on to second part. Did you share the screen when you did? And we move on to second part led by Ji-Hyuk Kim. No, he's here. So propulsion devices. Yes. 여기를 안 보이지? 눈도 눌러야 돼?
나중에 있어 솔직히 켜시고 그다음에 화면 공유 다시 하면 일단 이 켜진 건가요?
뭘? 네네네.
PPT 파일 먼저
열었지. 화면 공유도 열었지. 근데 여기가 안 보여지.
이게 지금 전 PPT 파일이 지금 공유되고 있는 것 같아서 일단 끊고 PPT 파일 먼저
열었어.
아 요건가요?
이건 아니군요. 들었어요. 포인트가 들어왔어. 왜 이래?
여기
아
이거는 어디 갈?
제가 지금 이거 스케줄 주문은 나오고
지금 혹시 화면 공유 해서 지금 화면이 안 되는 상태야.
유튜브 영상 같은 거 키는
그 지금 제가 이 화면 2를 통째로 보낼 거니까 유튜브 혹시 트실 거면은 유튜브 영상을 저 화면으로 드래그 하시면 될 것 같아요.
그러니까 여기도 있고 듀얼 모니터 쓰고 계시다고 생각.
그리고 잠시만요. 제가 소리 공유를 시켜서 하겠습니다. 툴에서 네 시작하시고
Hi everyone, my name is Chuyok Kim. I will begin my presentation on resistance and powering. In this presentation, I will be lecturing about propulsion devices. Reynolds number is defined by the following formula, which is a dimensionless quantity that quantitatively represented the relative dynamics between two types of forces, internal forces and viscosity forces, given specific flow conditions. A high Reynolds number implies low friction, leading to the development of vortices across a wide range of scales, resulting in rapid changes in momentum due to these vortices and a higher level of effective diffusion, also known as turbulence. Let's watch a related video to understand what it is. Next is broad number.
The Froude number is defined by the following formula, which is a dimensionless quantity representing the ratio of inertia to gravity in fluid flow. It is used when dealing with fluid motion affected by gravity and is employed to assess the hydrodynamic correlation of the flow. A high Froude number implies a reduced influence of gravity, resulting in large deformation of free surface, where the effect of static pressure becomes relatively small, particularly for planing and semi-planing ships. Through the following video, we'll take a look at a real-life example of demonstrating the concept of Froude number.
You can see a demonstration of the Froude number. When I turn on this sync, you can see the supercritical flow, which is here. It's very fast, very shallow. Then a hydraulic jump into the subcritical or tranquil flow, which then goes down the drain. Might be a little bit more pronounced if I turn it up a little faster. So there's that. You can
Now let's delve into propulsion devices. One of the most prominent examples is the screw propeller. A screw propeller essentially transforms rotational energy into forward thrust. As each blade cuts through the water, it generates a backward thrust. Screw propellers come in various types. First, there are solid propeller and controllable pitch propellers. As you can see in the diagram, the solid propeller has a fixed pitch, whereas the CP propeller allows for control the pitch. Additionally, there are supercavitating propellers and counter-rotating propellers. Let's watch this video for what is the controllable pitch propeller.
copy and paste it.
With DataCamp, you don't need to download Python to learn Python. You can learn right in your browser, with hands-on exercises for coding and data analysis, all in a way that makes data kind of fun. Go to datacamp.com and start learning for free today.
Massive ships are powered by massive propellers. Likewise, small boats are powered by small propellers, but the principles are the same. One propeller is the controllable or variable pitch propeller, but how exactly does it work? This vessel is the Hermes. She's an old design deep-sea salvage tug fitted with two propellers. I don't know what her original propulsion was, but I can use her for this demonstration and give her one controllable pitch propeller and one fixed pitch propeller. When they're spinning away like this, it's hard to see anything much, so let's slow it down and look at the controllable pitch. Like this, she's running ahead. The propeller blade is cutting the water and propelling it backwards. This is no different to a fixed propeller. When running ahead, they look exactly the same. The difference comes when we want to reduce the speed. To reduce the speed of a fixed propeller, you have to slow the rotation. Very easy if you've either got a gearbox or an engine that can easily vary its speed. It's a bit harder when your engine likes to run at a constant speed. A controllable pitch propeller, on the other hand, runs at a constant rotational speed. To reduce the vessel's speed, you change the angle of attack of each blade instead. It's hard to see while rotating, so let's stop it and have a closer look. Running ahead, you can see it's got a steep angle of attack. This makes it harder to turn, but generates more thrust. As you reduce the angle of attack, the engine has an easier time turning the propeller, but it generates less thrust, slowing the vessel. You can generate zero thrust by setting the pitch to 0. For example, this setting would be used when a ship has started her engines but is still alongside her berth, not yet wanting to move. By contrast, to set a fixed pitch propeller to generate zero thrust, you literally stop it. For a stern propulsion, a fixed pitch propeller needs to turn in the opposite direction. Ships do this either through a gearbox arrangement or sometimes by literally stopping the engine and restarting it in the other direction. The controllable pitch propeller just needs to alter its pitch to be pointing the other way. If we stop it again, you can see the alteration becomes a lot clearer. The shallow angle generates lesser stern thrust, but you can increase it by altering the blades even further. One thing to just compare quickly is the path that the water is directed down. Going astern, you can see the shape of the blade is less efficient than it was when going ahead. This is why ships' astern power is sometimes up to 50% less than for the same pitch ahead. Fixed pitch propellers, on the other hand, don't suffer quite as badly, as they are effectively always at their maximum pitch setting. The main takeaway point is that a controllable pitch propeller is constantly spinning. It's constantly generating a bit of water flow at the stern of the vessel. When handling a vessel at slow speed, that's enough to actually start a turn and throw you out of position. We call this effect transverse thrust, or propeller work, but that is a topic for another video. Hopefully in this video you've seen how a controllable pitch propeller works and what it means if you have one on your boat. You're in the middle of the ocean, sinking. As your vessel slips beneath the waves, your only hope is that your life raft will do its job and appear at the surface. You're completely reliant.
Now let's look into cavitation and explosion in propellers. As the flow speed increases, it creates a low pressure zone. This phenomenon causes water to reach its boiling point even at a relatively low temperature. It occurs locally in a pump, on propeller blades, and hydrofoils. 파워포인트 꺼져가지고 되겠죠? 네. 옆에 떠 있습니다.
Team City will help you to get started with continuous integration for free. Every big thing starts small.
One of the solutions to address this issue is the supercavitating propeller. The supercavitating propeller is variant of a propeller for propulsion in water, where supercavitation is actively employed to gain increased speed by reducing friction. They are being used for military purposes and for high-performance racing boats as well as model racing boats. Let's explore this further through a video demonstration.
Yes! If you can't beat it, use it! For high-speed vessels, sometimes cavitation is unavoidable. The propeller simply must pack a high thrust into a small area. These specialized cases call for supercavitating propellers. Now, the supercavitating propeller does not prevent cavitation. Instead, it guarantees cavitation, but more importantly, it guarantees it in a predictable pattern. So remember, the cavitation is only dangerous when the bubble collapses. A supercavitating propeller works carefully to ensure that the bubble never collapses until it leaves the propeller blade. These propellers show a distinctive wedge shape when viewed in cross-section. That wedge-shaped cross-section means that the pressure continues to drop as the bubbles travel across the blade face. If the pressure keeps dropping, the bubbles never collapse until they leave the propeller blade. The propeller remains safe from cavitation damage, even though it's causing lots of cavitation. Treat cavitation like any other natural disaster. If you understand it, you can avoid it. Careful propeller design limits cavitation to only minor levels of sheet cavitation. Armed with this video, you will now be able to recognize the various signs of cavitation and what they mean. Forewarn
The table summarizes the characteristics of each propeller under the supercavitating propeller section. It's noted for its strength in increasing speed by reducing friction. It's used in military application and high performance racing boats. However, it is mentioned as a disadvantage due to its high cost. What other propulsion devices are there apart from the screw propeller? Other propulsion devices include paddle wheel, air propellers, cyclotron propellers, and magnet to hydrodynamic propulsion. I will be presenting videos on each of the three propulsion devices mentioned. So this is the paddle wheel. This is the air propeller.
유라 한매가 언제까지 내가 니를 돌봐 줄란가는 모르겠다마는 니를
And this is the cycloidal propeller. And let's watch what is the cycloid propeller in this video. I think cycloidal propeller can move to right direction.
먼 미래 수백 년간 이어진 자연의 손으로 극지방의 빙하가 녹으며
Magnetohydrodynamic propulsion is a method for propelling vehicles using only electric and magnetic fields with no moving parts. Accelerating an electrically conductive propellant with magnetohydrodynamics. The fluid is directed to the rear, and as a reaction, the vehicle accelerates forward. This is a brief video introducing the principle of magnetohydrodynamic propulsion.
MHD stands for magnetohydrodynamics, also called magnetofluid dynamics or hydromagnetics. It is the study of the magnetic properties and behavior of electrically conductive fluids. While technically MHD refers only to water, hence hydro, the meaning has evolved over time to refer generally to all electrically conductive fluids. MHD propulsion utilizes electromagnetic forces to move fluids like ionized air, plasma, and seawater without the need for propellers or any other kind of airfoil. In fact, without the need for any moving parts whatsoever. The working principle of MHD propulsion involves the acceleration of an electrically conductive fluid by the Lorentz force. The Lorentz force is the repulsive magnetic force appearing wherever an electric current is perpendicular to a magnetic field. Be sure to check out our full video link in the description.
Like the image shows, it's possible to create a simple model utilizing this principle. However, practical implementation is still the developmental stages. This video is how the magnetohydrodynamic propeller operating. Thank you very much for the presentation.
Is that? We move on to the discussion session. Okay. Okay. Discussion session file is here. 네. 이거를 전체를 화면이 전체 화면 하는 거 싫을 텐데 그러는 게 편하실 텐데 이게 전체 화면인가?
전체
모든 화면. 화면 1인데
전체군요.
응.
화면 2가 하십니다.
이게 전체 화면?
네.
아니잖아.
여기 화면이 이제 다 송출되고 있어. 그럼 요거를 뒤로 옮겨서 제가 하면 돼요.
무슨 말인지는 못 알아듣겠어요. Okay. Let's get started our discussion session for propulsion device and model test. My first question is why model test is necessary? In the real industry, we use a lot of model tests, and why is it necessary? And why we are doing model tests? Do you have any idea?
To use model tests to be sure that our calculation were right before making the full prototype and to real scale ship.
Yes, that's right. And is there any other ideas? Okay. Is there any ideas? Why model test is important and why we are doing this? Yeah, because simulation cannot show the complete scope of reality. Yes, that's true. We cannot do everything from the computer fluid dynamics, so we are making a scaled model and test it from the water, test it in the water. And any other ideas? I think the reason we are doing simulate model test is to sure before we cost a lot of money, we have to be sure this is right and this is safe and this will not be fail. So I think model testing important. And the next question is model test reliable? We can scale it to the model, and we are not sure this effect. Yeah, safety issues, yes. And when we scale it to the model, the physical phenomenon in the model test it might not fit in the real size scale, but we believe that model test is reliable. Why model test is reliable? Mm. Or you can talk through the Zoom. The one reason that we can rely on the model test is because fluid dynamics is fluid dynamics. We can scale it through the similarity of the systems. So we can scale it as velocity in same scale, or the length and the volume is scaled and volume scales. So I think this is because we can scale it. And is there any ideas?
Thing that you have just said, that, for example, we can use different fluids, water, for example, to test it to change the viscosity in respect, for example, Reynolds number or fluid number. And thanks to remains in this scale and these range of numbers, we can be sure that the model test is still reliable, even if it's not the good side.
Oh, thank you for your opinion. Can you say it one more time?
Yeah, I said that it was close to yours and your answer, but if we can, for example, modify the fluid that we are using to respect the Reynolds number, and so we can be sure that the model test is reliable, even if it's not the side.
Is it correct?
Yes.
Thank you. Any ideas? And we will go on to next questions. What are the pros and cons of model tests? I think one of the pros is we can make it in cheap cost and smaller scale and test it. And one of the cons is even if we try to make it similar as we can, but it might not fit in the real world. Is there any ideas?
Some space.
That's true. Smaller space, you mean? Cons, I think. It takes too much space, yeah. Any other ideas? Mm,
Maybe for the case that even if you are not making it at the real scale, making it at the time scale will raise some production issue, so you can be aware of that. Thanks to knowing this.
I think it'll be enough, and let's move on to the next question. And this is for the propulsion devices. What are the different types of propulsion? Just briefly give me ideas. So from the previous lecture, we know the propeller and pedal wheels, the cyclo-rotor, which is the perpendicular propeller, and what else? Through the whole history, what mankind used to for propulsion. Do you have any ideas? Jet propulsion, yes, that's right. Jet pumps. And let's go to the ancient level. Mankind use oars. And what else? Through the mediation level in 17th centuries or some people. Windsail, yes. And there's some interesting ways that oscillating flappers which is flapping like this, like when we do at the swimming. Okay. And let's go to the next question. What are the different propulsion systems we use in the modern ships? This is the propulsion devices, maybe the propeller, and which is the powering system. Yeah, which power came from? I mean, what power does it rotate the propeller? Yeah, you say electricity. And the most widely using is diesel engine. And what else?
Ships are going back and using winds.
Winds, yes, that's true. And in the Navy, some ships, some submarines using nuclear powers. And actually, in this level, we can use any other power generators for propulsion, because we make electricity and make those electricity goes to the propeller. So any other electric generating method can be used. So let's move on to the last question. And what is the pros and cons of each system? Let's go 1, 1, 1, 1, 1, 1, and let's finish. How about diesel engine? I think diesel engine's the number one pros is cheap. Yeah. And what is cons of diesel engine?
It's not friendly.
Yeah, it's not eco-friendly. Yeah, emissions. Okay. Let's move on to next. What's the pros of nuclear?
The durability, we just not so much.
With the little, yeah, high efficiency. Yeah. And what's the cons of nuclear? Definitely.
It's really hard to integrate, so it's really expensive.
Yeah, expensive. And the one thing is pollution. Okay, let's go to the gas turbine. Gas turbine is like an airplane engine. Some of ships using gas turbine for their propulsion. And what's the pros of gas turbine? We can think it similar with the airplane. I think as we think of the airplane, I think one of the pros of gas turbine is it's really quickly turned on and it quickly generates a high power and it stops very quickly. Yeah. And the cons is it takes a lot of fuels. And do you have any ideas? Yeah. Yeah. Yeah, it's similar with airplane, so it takes huge spaces. That's true. But when you compare with the diesel engine is the size of the building, so it might be smaller than. And I think one of the cons of gas turbine is it takes a lot of fuels to generate powers. And what's pros of LNG engine? LNG engine is similar with diesel engine, but it uses LNG. So what's the pros and cons of it?
Maybe one of the causes is that the LNG is harder to store than plastic diesel.
Yeah, that's true. So we're not ready for the LNG. So LNG station is not around the world. So that's true. Uh, and the chatting said is eco-friendly. LNG emits a much lower CO2s than diesel, so it is eco-friendly. And I think this LNG engine's pros and cons are upside down of the diesel engine. So it's true that the lack of storage, and one more thing is it is expensive. What about Stirling engine? Some of ships use Stirling engine for the high efficiency, but because we learned that Stirling engine is the secondary high efficiency system in the world. So the pros is high efficiency. And what is the cons of the Stirling engine?
Maybe it's not enough powerful.
Yeah, it is very slow to get high power, and is not that powerful, so it doesn't go faster. And the last two, the hydrogen means it is engine but using hydrogen, and the pros and cons are similarly LNG. So hydrogen engine uses hydrogen for its propulsion. So hydrogen engine doesn't have any emissions. So it is very eco-friendly. And what is the cons of engine? Hydrogen engine.
Liquid hydrogen, there is a lot of pressure to store.
Yeah, that's true. Requires high pressure. And when we pressure it to the liquid form, we use electricity too. So it doesn't that much eco-friendly, Mike. And the one thing more is hydrogen it has very low energy volume rates. So we need a lot of hydrogen for propulsion. And lastly, how about the electricity?
It's really powerful.
Powerful, yeah, it's true. And what else? Any pros and cons?
On course, you have to have a lot of batteries, so you don't have good range. You can go really far away from your house with a big stuff.
Can you explain one more time?
Yeah, you need batteries.
Yeah.
And still ready, so currently you can make big trip with only electric engine.
Yeah, that's true. It requires battery, and batteries there is capacity is not enough, you mean? One thing that I think electricity is not good is battery is also heavy and it takes long time for charging. And this is the end of my discussion session. Thank you.
Thank you very much.
All right. We have a technical problem through the classroom. I hope you can hear and listen from the speaker. All right. Any other questions? And who are coming to tomorrow's visit? See you tomorrow. Otherwise, next week we will have a project presentation, final one. All right. Bye now.